Good morning. My name is Rem Tontino, and on behalf of my team, under Dr. Borodowski, alongside my teammate Caleb Bernier, we'll be presenting to you today our definition, analysis, and approach to problem 1. Currently, there are no reliable pancreatic cancer screening methods that could detect the cancer at the earliest stages. However, pancreatic cancer is most treatable in stages 1 and 2. In stage 1, though, there is a 10 to 15 year dormant period where the cancer is asymptomatic. Patients don't observe any symptoms, which is part of the problem. Also the location of the pancreas makes detection of tumors difficult.
Our goal is to accurately detect pancreatic cancer in the earliest and most curable stages by finding a screening method that improves sensitivity without sacrificing specificity. In order to do this, we asked ourselves 4 main questions, and this led us to create a model for the screening process. We also were able to look into current methods being used and where changes need to be made in the future.
So the 4 questions that we asked ourselves when approaching this problem were when to start screening, who to screen, what should we use to screen, and how often should the screening be done.
This is what we came up with for our model. So we start with the patient's medical records. This includes their genetics, their family history, their lifestyle, and their health records. We then take this information and put it into an initial information processing method, which we created, which is a score based off the relative risks. We then know that we can't screen an entire population, so we broke these patients into 3 groups. Our low risk group does not need to be screened. Our moderate risk group, we recommend screening, and then our high risk group, we strongly suggest screening. Every patient that agrees to be screened is then put into our first test of an EUS. The positive test result would then move this patient into a MRCP test. Again, a second positive result would send this person to the diagnostic and the recovery stages. Once a negative result is seen, though, a patient of moderate risk would be recommended to return every 3 years to be screened, and a patient of high risk would be recommended to return every year to be screened. In order to use this model, though, we need to ask ourselves, when do we start using it? To begin, we found that our research concluded your age plays a factor in your probability of developing pancreatic cancer. So many institutes use the threshold of 40 years to begin the process of screening. However, we recommend if you have a family member with PC, you begin the screening process 10 years prior to the age to which they were diagnosed. And if you have Peutz-Jeghers syndrome, we suggest you start screening at the age of 30.
So to better answer our second question on who to screen, we first have to identify our high-risk populations. And how do we do that? We find out the risk factors associated with these high-risk populations. Then by taking that, we get our probability, our audience that has a high probability of contracting the pancreatic cancer. And by doing this, we limit the error that's caused by screening the wrong populations. And in doing so, we increase the sensitivity without decreasing the specificity.
Here we have all the factors that went into our model. At the top, you can see the Peutz-Jeghers syndrome with the highest relative risk, so that was weighted the most. You can also see that the number of family members with PC play a role in the high risk and the moderate risk factors. Also, your development of any other certain types of cancer play a role in your probability of developing pancreatic cancer. And then for low risk, we have some things such as smoking and type 2 diabetes.
So how are we going to get all these risk factors and identify the levels of high, moderate, and low? So what we did is we created a MATLAB function that assesses all the different kinds of risk factors that a patient will have, and in total it will give us our net risk for that patient. So as we go to the script, we have a screenshot of our MATLAB script. Into the MATLAB function, we have inputted every single risk factor that was associated on the previous slide. Each of these risk factors is weighted at their certain risk factor. By answering, this is a simple question test, by answering a yes, the function multiplies the value of the risk factor by 1. By answering no, it multiplies the value of the risk by 0. At the end, the function compiles all of the risk factors and adds them together to make your gross raw risk factor score. However, that's not the one we're going to use. Actually, we're going to scale it down by dividing it by the total risk available, which is 291. And by doing so, and multiplying by 100, we can get our net risk factor total from a scale from 0 to 100. And by determining this, a score of over 45 will be a patient with a high risk of pancreatic cancer. From 20 to 44 would be a moderate risk, and less than 20 would be a low risk for pancreatic cancer.
As an example, we have our case study of Jane Doe. She is our patient with Creutzfeldt-Jaeger syndrome. She also has cystic fibrosis and type 2 diabetes. Her heritage is Ashkenazi Jew, and they have a history of breast cancer. Her brother also has PC, and recently she began smoking.
So how are we going to put this in our model? First, with all this genetic information and family history, we put this into our MATLAB function. We put in all the values of the risk factors that she has, and her total net score ended up being 181. Divide that by 290, she gets her and multiply by 100, she gets her adjusted net score at 62, which puts her in the high range for pancreatic cancer. So we'll now have to go to the screening and the diagnosing method. And so, what did we use to screen? First of all, after conducting our research initially, we approached Dr. Basil L. Reyes, a pancreatic cancer researcher and oncologist at Emory University. We asked him what diagnosing methods work the best, were most efficient, and also we asked him where the future of these diagnosing methods are heading.
So this is a table of the methods that were competing for our model, however we ruled them out. CT scan was ruled out due to its non-specific imaging. The PET scan and the fusion of the PET-CT scan were ruled out due to their high cost and their low availability. We also ruled out biopsy because it is mainly used for confirming and not screening. So now we would send our patient to our first test of an EUS. This would lead the doctor to be able to control what he's looking at and also gives a real-time image. This test, in relation to others, is non-invasive and is low in cost. The specificity for this test is 96% and it is 84% sensitive. If the test was positive, the next test the patient would go through is an MRCP test. This is specialized for the pancreas, and again, is low in cost and non-invasive compared to the other tests we looked at. The specificity is 97% and it is 84% specific. Although this is what we can recommend right now for current methods, we know something needs to change. So future methods need to shift our view and start looking at molecular changes. We need to look at mutations on the genetic level, such as the RAS gene and P53, along with the X and Y genes. But in order to do this, we have to ask, how are we going to do this? So we suggest we need to start identifying somatic mutations in the pancreas through the pancreatic juices, and also we suggest screening the blood for protein signatures.
So a new kind of future way, great example of screening blood for protein signatures, was conducted by Jack and Draka and a team of Johns Hopkins researchers. They basically used a novel paper sensor test to detect the presence of mesofilm in the blood using the conductivity of carbon nanotubes on paper. And this test was extremely cheap. It was $3 to conduct. It took 5 minutes just to analyze and diagnose the data. Also, I know this is a small sample size, and this is later down the road. There's still research being done on this study. Just in case, Boston College also did a research on this and found similar results. But in 200 trials, the specificity was 100%, and sensitivity was 100% as well. So, in conclusion, based on our research, we have identified the high-risk populations by analyzing the risk factors and putting them into our MATLAB function.
We were also able to answer our 4 starting questions. So when do we begin the screening? We recommend 40 years of age. And we also identified who we are screening, the high-risk populations found through our MATLAB. Then we were able to identify which methods to use, and we recommend the EUS and the MRCP. And finally, we found the frequency in which these patients should be screened.
So for the future, our team recommends that screening should be looked at the molecular level and identify changes that can only be observed in stage 1 of the pancreatic cancer. Once these changes are observed, we can prevent the cancer and give the patients the 10 to 15 year period where they could fight off the cancer, which can potentially save more lives. I'd like to thank all of you for your time. All right.
So in your risk factor algorithm, you have a total of 14 questions.
Yes.
Do you really think that's sufficient to determine?
Okay.
But also you don't include age, which is a major factor. Someone's.
All right. Okay, so first of all, age is the preliminary step before using this. Once we have age, then we're going to use this MATLAB function. Also, the MATLAB function is dynamic, which means we can add more risk factors that arise. We can adjust the variables. The function is very easy to work, and once you run the script, it's just putting yes or no.
However, these are also the risk factors that we found most common and consistent through our papers and research. In order, you can't just throw in a random risk factor that only one group has found related. You need more backup to that risk factor to include in such a great population.
All right.
You define those thresholds for low risk, medium risk, and high risk. Do you have like any reason for doing that?
Yeah. So we based that off of the Peutz-Jeghers syndrome. Obviously, this is related to the highest, and through our research, we were able to see that if you have Peutz-Jeghers syndrome, you're almost 100% likely to develop pancreatic cancer. So if a patient alone only has Peutz-Jeghers syndrome, they're in the high-risk group. So based on that threshold, anything that we consider 45 or above, because when you plug that in, the score would be 45, that is our high-risk group. And when you add all these factors together, it moves the patients through.
Sorry. All right.
Interrupt real quick.
Yes.
All of the groups have mentioned the PJS syndrome, but nobody's described what it is.
Peutz-Jeghers syndrome is a disease which there are tumors or tumor-like cysts that form on the GI tract, which also in turn affects a protein and a gene that is also related to the pancreas, which causes cancer to form.
I just want to say, my question was more, I know that you define that as 100, but why 45? That's just seems like a random number.
Okay, 45 was associated with the Peutz-Jeghers syndrome. When we, like I said earlier, the value is 132. Overall, the total of all the risk factors was 290. 132 divided 290 times 100 gave us the 45. And since we already knew that Peutz-Jeghers syndrome, you have I think it was like a 99.7% chance to get a cancer, almost 100%. We knew that since the threshold that they got was 45. We knew that 100% chance of getting cancer was close to 45.
But I decided to skip with the biomarkers and then go directly to scanning methods.
Why we skip biomarkers? Good question. Biomarkers, there's a plethora of biomarkers out there, but we found that they were widely inconsistent. There's so many out there, and that there's so few tests done, and biomarkers, just like the specificity and sensitivity would fluctuate. Also, some biomarkers are just not solely for pancreatic cancer. Some biomarkers are related to breast cancer, lung cancer, and all those other things. So biomarkers would not be as accurate as what we've proposed.
However, there is a promise for the future, and that's where we are suggesting you going. By using the mesothelin, as the Jack and Draka did, that's going in the direction of the biomarkers. It's just, we don't recommend that right now based on the current tests that have been run because of the wide range of specificity and results found.
So back to the relative risks, why were you adding them up? Because if you take hereditary pancreatitis, cystic fibrosis, and familial pancreatic cancer, if they have all three of those, they still have less of a risk than if they just had Peutz-Jeghers syndrome by your algorithm.
Okay, so what we did, the risk factors are based on the scale that makes us able to add these independent factors together. And we can see them in comparison side by side. So in order to use that in our MATLAB, they had to be on the same scale and then scale down to the same size, if that makes sense.
So the previous group had mentioned that it takes about 11 within 12 years, for the cancer to, the gene mutation to form, and then to actually be able to see some sort of mass or to develop cancer. So if you're looking at the high, medium, and low risk categories, wouldn't you kind of want to target the low risk categories? Because I have family history of prostate cancer, but I'm a female. I don't have any other female cancers. I don't have anybody that has CF or anything else, but I'm terrified of getting cancer. So I would fall totally into that low category and probably come up low for the next, few 10 years, but that cancer could be developing right now.
Yeah.
So
That's
I
good.
mean, it seems high, if you're already in the high risk category, you're already there.
Yes. Okay, that's a good question to, that's been asked, addressed. Our method right now for this initial part was for the current methods. What we want to look out for the future is what you said earlier, the 10, 15, or that 11-year dormant phase where you can actually look at the genetic mutations. In my interview with Dr. Reyes, he's done research on this. Right now there are no machines that could detect mutations in genes such as BRCA2, which is also linked to breast cancer, also the X and Y chromosome genetic mutations, and also the PR5. Right now there's not any machines that can do that, but that was not our problem. Like that's a good question for another problem. To find a machine or device that could determine these genetic mutations at such an earlier stage. So at this 10 to 15.
And also, if you start screening people for every little detail, your population you're screening is going to grow. And right now, with like all the technology out there, there's just not enough to screen such a big population. So to increase the specificity and sensitivity, we're looking at the risk of the group of people that are at the highest risk. And that will also lead to more studies of like who's going to develop it, and then you can expand to those earlier stages and what to look for.
Kind of pretty sure.
Can you give your evaluation of paradigms?
Okay.